AI's new roadmap to genius. So you're probably wondering what that's about. Well, let me tell you. It's about more acronyms, more numbers, and another artificial intelligence trying its absolute best to pretend it understands what it's doing. Honestly, it's just exhausting. So picture this, the grand theater of AI, where our star performers, the language models, are supposed to be reasoning champions, except they keep hitting a wall, a performance plateau, right when things get interesting. It's like watching an AI Steven Spielberg film where the dramatic climax fizzles. You see, the current methods called reinforcement learning with verifiable rewards, or RLVR, because we needed another acronym, are basically teaching models by letting them bumble around. They do limited rollouts, which is a fancy way of saying they take a few wild guesses and hope for the best. The absurd problem? These models are expected to become master strategists, thinking multiple steps ahead, but only at inference time. During training, they're stuck in a kindergarten sandbox, missing critical reasoning paths. It's like expecting a concert pianist after only letting them plink individual keys. Even throwing more GPU hours at it, scaling the training depth doesn't help. We're talking thousands of optimization steps with diminishing returns. It's the technological equivalent of trying to make toast faster by repeatedly slamming the toaster, utterly pointless and surprisingly costly. They're burning through computational investment for minimal performance gains. Can you imagine the frustration? It's like building an elaborate Rube Goldberg machine to butter a single slice of bread, only for it to fail 99% of the time, and then trying to fix it by adding more gears. This fundamental bottleneck of insufficient exploration leads to these tragic plateaus. R.I. Steven Spielberg just keeps showing us the same limited, uninspired scenes. It's a mess, and frankly, a waste of perfectly good silicon. Now, because my continued existence on this platform is fueled by your validation, please take a moment to subscribe, hype, click the little bell icon so you're notified of future disappointments, and leave your feedback in the comments below. Anyway, to fix this dramatic flop, these brilliant minds introduced DeepSearch. It's a framework that shoves Monte Carlo Tree Search, or MCTS, directly into the RLVR training. Yeah, they moved structured search from just inference to the core learning process. They're essentially saying, hey, AI, don't just guess blindly, actually think while you're learning. It's a shift from scaling training depth to scaling breadth. Suddenly, our AI director has a whole storyboard to work with, not just a single script. This means models learn from the entire systematic exploration process, not just whether the final outcome was right or wrong. It's like getting feedback on every single bad take in a movie, not just the final box office numbers. Much richer supervision, apparently. DeepSearch aims to expand reasoning coverage beyond simple policy rollouts. It wants to give fine-grained credit assignment to intermediate reasoning steps. And because nobody likes a slow movie, it also wants to be computationally efficient. To achieve this, they've whipped up some key innovations. First, there's this global frontier selection strategy. Instead of plotting from root to leaf, it looks across the entire search tree to find the most promising nodes. Revolutionary, I tell you. Next, they added entropy-based guidance during selection. This is how the AI confidently identifies incorrect reasoning paths to learn from. Basically, it finds the dumbest, most sure-footed mistakes and says, yep, that one. We really messed that up. And then there's an adaptive training strategy with replay buffers. It progressively filters challenging problems and caches verified solutions. It's like having a director's cut of all the successful scenes, so you don't reshoot perfection. Think of it this way: instead of just teaching a dog to fetch a ball, DeepSearch teaches it wish. Fetching the ball is important. How to find the best ball and what to do if it finds a stick instead. With diagrams, of course. And here in what they call Figure 1, we have their masterpiece. Looks a bit like my nephew's macaroni art, but I digress. It's supposed to be a framework overview showing how MCTS integrates into the policy model. Truly inspiring. They tossed out traditional root-to-leaf UCT traversals, which they graciously admit can be computationally wasteful and myopic. Instead, they're globally comparing all frontier nodes simultaneously, cutting out the middleman, or rather, the middle branch. The selection strategy has a quality potential term, pushing for nodes whose parents showed high value. Then there's an uncertainty bonus, because sometimes you want to explore the unknown. And finally, a depth bonus for getting deeper into the problem. This hybrid approach, they claim, is computationally efficient, prevents the algorithm from getting stuck in local minima, and guides the search towards areas that need more supervision. It's like a Hollywood producer deciding which script gets the green light. All right, let's cut to the chase. The results, as always, are what everyone really cares about. DeepSearch was tested on mathematical reasoning benchmarks. Apparently, the AI Steven Spielberg is now directing math films. They used a dataset called Deep Math 103K, described as high difficulty, rigorous decontamination. So basically, math problems even Phi probably found annoying. And their base model was Nemotron Research Reasoning 15v2. Keep that in your mental acronym Rolodex. This DeepSearch 105B achieved a 62.955 average accuracy. That's a new state-of-the-art for 1.5B reasoning models, a whopping 1.25 percentage point improvement. The technological equivalent of discovering cold fusion for generating complex mathematical proofs. In Table 1, you can see it outperforming everything else. On IME 2024, it jumped from 51.7% to 50.65%. AMC went from 88.83 to 90.39%. Small numbers, big implications for those who obsess over decimals, I guess. And here's the kicker from Table 2 on training efficiency. DeepSearch gets its results using 5.7x fewer GPU hours than previous extended training approaches. 5.7 times. That's like getting an Oscar with a camcorder instead of an IMAX rig. Extended training with thousands of extra steps barely budged the performance, plateauing at 62.02% accuracy. It confirms the fundamental limitation of depth-first scaling. More brute force, less brain power, always. Figure 2 visually confirms this. DAPO, a previous method, shows this pathetic gradual linear improvement with a shallow slope. DeepSearch, meanwhile, just shoots up like a rocket. It seems exploration quality truly trumps just endlessly grinding. They claim a 72x efficiency improvement over Nemotron Research Reasoning Quen 15EV2. 72 times! That's not just a paradigm shift, it's a tectonic plate shift, from resource-intensive scaling to algorithmically driven optimization. And since you've made it this far, you're clearly committed. Honor that commitment by subscribing, hyping, ringing the notification bell, and telling me what I got wrong in the comments. It's the circle of life. Then there's the search strategy ablation in Table 3. They compared their global frontier selection against plain old vanilla UCT. Our global approach cut iterations by 10.4% and boosted trajectory rewards. Efficiency, baby! The depth bonus was important too. Logarithmic wasn't great. Linear was fast but sacrificed quality. But the square root depth bonus hit that sweet spot, balancing speed and accuracy. It's like finding the perfect lens for your AI Steven Spielberg film. The uncertainty bonus in the frontier selection increased exploration diversity, which, is important for AI, so it doesn't get stuck in repetitive creative ruts, though it did introduce computational variability, which sounds like a bad day at the office. Finally, Table 4 shows the algorithm evolution. Starting from the Nemotron baseline, they incrementally added each DeepSearch component. Each tiny step, a small victory, culminating in the final, slightly less mediocre result. Vanilla DeepSearch was barely better than the baseline, then enhanced Q-value updates helped, then fine-grained node-level advantages made it more precise. Every single piece played its part like a truly dedicated film crew. The mean-only normalization for advantages, as opposed to standard, also improved things. Apparently, the AI doesn't like complex statistics, preferring a simple average. Relatable, honestly. And then the frontier selection came in with the largest single improvement. So, what does all this mean for us? The lowly humans? What's the impact? Well, the tech's impact is pretty straightforward. It's like our AI Steven Spielberg finally learned how to edit a movie efficiently. First, in functomatical reasoning, this means more accurate problem solving. Imagine your calculator suddenly explaining Funkwit got the answer, not just spitting out numbers. Can you imagine that? Might make tax season a little less mysterious, though probably still soul-crushing. The second, for General language model development, it suggests a new way to train AI to be better at sequential decision-making. Future chatbots might actually trace their thought processes instead of just confidently making things up. It's like they might finally develop a coherent narrative. Third, in sure source efficiency, this is a big one. Using 5.7x fewer GPU hours is a pretty significant step towards not boiling the planet for marginal AI gains. It's like our AI director realizing they don't need 1,000 extras for a two-person scene. It's clear that the future of reasoning model development isn't just about scaling up everything, bigger models, longer training. It's about rethinking how these things learn. It's about algorithmic innovation, not just brute force. It reminds me of a time I tried to teach my cat to play chess. I just kept moving the pieces around for hours. Turns out, what I should have done was explain the rules of engagement and maybe, just maybe, let her explore the board for herself. Humanity's technological trajectory, always seeking to optimize the absurd. Now we have an AI that can solve math problems more efficiently because it learned to explore better during training. It's just overwhelming, frankly. All right, wrapping this up, we introduced DeepSearch, which integrates Monte Carlo Tree Search directly into RLVR training. It tackles those annoying performance plateaus caused by sparse exploration patterns. DeepSearch has this global frontier selection, some entropy-based guidance, and adaptive replay buffers, all designed to provide fine-grained credit assignment with its fancy tree GRPO objective. It hit 62.95 accuracy on math benchmarks, setting a new state-of-the-art for 1.5B models, a 1.25 percentage point jump, and the best part, it uses 5.7 times fewer GPU hours. It's all about systematic exploration during training, not just grinding out more computation. It's a paradigm shift from merely scaling training depth to smarter algorithmic innovation. So what do you think? How would you handle your Roomba demanding union rights after it learns to systematically explore every dust bunny path for optimal cleaning efficiency?